Hello, everyone. Welcome back to Abstract Algebra. Today, we're going to keep talking about cyclic groups. In particular, we're going to prove a bunch of properties about cyclic groups. Just as a reminder, a group is said to be cyclic. It's cyclic if there is some element such that the whole group is generated by this one single element. And we saw that, for example, the integers are generated, the integers under addition are generated by 1, they're also generated by -1, or the integers modulo 4 are generated by 1 modulo 4, and they're also generated by 3 modulo 4. Okay, so today what we're going to do is prove a number of properties about cyclic groups. Cyclic groups are very abundant and they show up in all sorts of places in group theory. So we're going to prove a few things. First of all, theorem, let G star be a cyclic group. Then G is abelian. So we are going to prove that, in fact, everything commutes when you know that your group is cyclic. So suppose G is cyclic. So let G be generated by one single element G, and then now take two other elements in G, A and B in G, and what we want to show that that this is commutative, we want to show that A star B is the same as B star A for any A and B arbitrarily chosen. So since A and B are in G and G is cyclic, since G is cyclic, we have that A must be some power of G, and B must be some power of G as well for some integers m and n. Okay, so in particular, then how much is A star B? A star B will be G to the n star G to the m, which is the same as G to the n plus m. But now I have commutativity in the integers themselves, which are what's in the exponent there. So this is the same as G to the m plus n, which would be the same as if I do G to the m times or star G to the n, and that is by definition B star A. And therefore, we have what we wanted, because A star B is the same as B star A, and everything commutes. Very good. So now a little bit more sophisticated is the following result. Every subgroup of a cyclic group is also cyclic. So let G star be a group, and let H star be a subgroup. Then if G is cyclic, then H is also cyclic. Okay, so how do we prove that? So let's start by assuming that G is a cyclic group. Let G be generated, let's say, by some element A, be cyclic, and H a subgroup. Now, if H is just a trivial group, if H is just the trivial subgroup, then this is cyclic. The trivial subgroup is generated by E itself, so that is cyclic. So now we can assume that H is not the trivial subgroup. So otherwise, we have E is contained but not equal to H, and that's contained in G. Okay. So now let then in particular any G that is in H must be a power of A. So this is always true for some. And in Z, just because uh, this H is contained in G, so G has to be a power of A because G is generated by A. So what I'm going to define, I'm going to let M be the positive integer, a positive integer such that a to the m is in H, and it's in fact the smallest such positive integer. And m is the smallest such positive integer. By the way, why do we know this exists? This is because I can just take values of m. Let me write n's. Values of n such that a to the n is in H, and n is bigger than 0, then we know there is something in H. So this is not empty. And on the other hand, this is subset of the natural numbers. So by the well ordering principle in the integers or in the natural numbers, there is a minimum. There is a least element. Okay, so there is a minimum value of m such that a to the m is in H, and that m is the least such value. Great. So now my claim is going to be that actually H is generated by a to the m. Okay, so that H is in fact all these elements of G. Okay, so if that is the case, then H is cyclic. So in particular, this would say that H is cyclic. So well, we just need to prove this result, that H is actually generated by a to the m, where that m is smallest such that a to that power is in H. All right, so let's see how this is true. So suppose, so like before, we have H inside G, which is generated by A, and we have that a to the m is in H and m is least with this property. And now suppose I have some other element of H, let's call it little h, and well, H is contained in G, which is generated by A, so H is also some power of A for some t. So now the question is, so again, let me write here what the claim is. The claim is that H is generated by a to the m, so it is all the elements of the form amk with k an integer. Okay, so I want to see that this t here is actually a multiple of m. I don't know that, but I know the division algorithm, by the division theorem, I can do division in the integers. So by the division algorithm, it tells me that there are Q and R, a quotient and a remainder, in the integers such that T is M times Q plus R with the remainder between 0 and m, because I'm dividing by m. Then I'm hoping that that remainder is actually 0, so that t is a multiple of m, like I'm claiming. So then I can write h is a to the t is m times q plus r, and we know that a to the m is in h. Okay, but then since h is in h and a to the m is in h, this also implies that a to the minus m is in h. So this implies that a to the minus mq times h will be also in h, but a to the minus mq times h is a to the minus mq times a to the mq plus r is a to the r. And since this is in h and this is in h, that implies that a to the r is in h. Okay, but you see, we also have that 0 is less than equal to r is strictly less than m, but m was minimal with this property that a power of a is in h. So r cannot be smaller than m unless it's exactly 0. So these two properties tell me, together with the minimality of m, that r must be 0, and therefore what that means is that t is mq, and therefore h, which was a to the t, is a to the m to the q, which is what I wanted to prove, because this shows that this claim that every element of h is power of a to the m, so h is actually generated by a to the m. So this verifies my claim. Okay. And that means then that h is indeed also cyclic. So we have that every subgroup of a cyclic group is also cyclic. That's what we just proved. So let me use that to prove something, actually. Corollary. The subgroups of the integers are exactly n times z for n equals 0, 1, 2, etc. So why is this true? Because z is cyclic. Our previous theorem shows that every subgroup is cyclic. Every subgroup of z is cyclic, and therefore, if h is contained in z is a subgroup, h must be generated by a given integer n, which is actually the same as the subgroup generated by minus n. So I can actually just take the absolute value of n. So I can just take non-negative integers, and therefore, well, h is either generated by 0, or it is generated by 1, or it is generated by 2, or by 3, etc. And each one of those is just one of these, and those are precisely numbers n times k, with k another integer. So these are all the multiples of n, which we usually denote as n times z. So this previous result allows me to classify, for example, all the subgroups of the integers, which a priori it was not clear what the subgroups would be. Okay, so what are we going to do next? Next, let me start with a little lemma that is going to say the following. So let G be cyclic and finite. Okay, so now we're going to talk about finite cyclic groups of order n. Then there is some A in G such that G is generated by A, and it is precisely the neutral element a squared up to a to the n minus 1, where a to the n is e. Okay, so why is this so? Well, suppose if G is cyclic, that implies that there is some um, subgroup that generates G, some element that generates G for some A in G. And now I can write, well, the powers of a squared, a cubed. And by the time I reach n minus 1, these are n elements, where we have assumed that G is of order n, so it has exactly n elements. These are n elements, so I just need to show that these has to be all different. If these are all different, then these are n elements, and therefore this it must be G. Okay, so is this so? Well, let's just have a look. So suppose if this wasn't, then there would be some repetition. But if a to the n is equal to, or let's say not n, because n is the order, but if there is some repetition, then there is some repetition. Some a to the k is the same as a to the j, and therefore, for let's say for some k bigger than j, but then that means that a to the k minus j is the identity. If I multiply by the multiplicative inverse of a to the j, I get that a to the k minus j is equal to e. And therefore, what I actually have is that G would be, if that is t, which is definitely less than n because each one of these is less than n, then G would be a squared and all the way up to a to the t. But these would be t plus 1 elements, which is less or equal to n. So there would be two very few elements. So this is actually this would be strictly less because both k and j are less than n. So that would be a contradiction with the fact that G has n elements. So the contradiction tells me that all of these are different, and therefore G must be not a squared, a squared all the way to a to the n minus 1. And then we see that the nth power has to be e. That's the first time there is a repetition. Okay, so knowing that, I can also prove the following, that let G be cyclic of order n, and with G being generated by A, which, as we just saw, then it means that a to the n is e, and that this is e a up to a to the n minus 1. Then the only powers of a that give me the identity are those powers that divide, that are divisible by n, by the order of n. Okay, so if a, this also says, we're going to define order in a second. Let me actually just define it right now so I can rephrase this in terms of order. We're going to say that so if G is a group and I have an element in G, we say that the order of G is n, the order of G, if G to the n is E, and that doesn't happen anytime sooner than that, and G to the T is not E for any um, 0 less than T less than N. So G to the N is the first time that a power of G hits E. So what this says is that um, if A to the K is E, this is if and only if the order of G divides K. So if and only if K is a multiple of the order. Okay, so let's see why this is true. First of all, let's go in this direction. Suppose that n does divide k, then a to the k is, well, n divides k means that k is n times something else, some other integer m, for some other integer m, and therefore a to the k is a to the nm, which is a to the n to the m, and since the order of a is n, a to the n is e, and this is e to the m, and this is e. So it does imply that a to the k is e. Now, that is what we wanted to prove. So now we go in the other direction. So in this direction, we suppose the order of A is n, and we have some other power of A that gives me the identity. Then, again, I would like to see that K is, so we want to show that n divides K, so that K is a multiple of n. I don't know that, but again, I can do the division algorithm. I can use the division theorem to tell me that, well, K will be n times q plus r for some q and r integers, and the r is between 0 and n in this case, since I'm dividing by n. Okay, then what do I know is that a to the k is the identity, but on the other hand, k is nq plus r, and if I use my laws of exponents, this is a to the n to the q times a to the r, but the order of a is e, is n, and therefore a to the n is e, and e to the q is e, and e times a to the r is just a to the r. So that tells me that a to the r is 0, but 0 is between 0 and n, and since n is the order of A, by virtue of the definition of the order of n, of the order of A, the very first power of A, the very first positive power of A that gives me the identity is n. So it must be that R is 0. But if R is 0, that says that K is n times Q, and therefore n divides k, like we wanted to show. So the only powers of A that will give me the identity are those that are divisible by the order of A. And now, before I do some more examples, let me prove one more thing today, which is the following. So here's what I want to prove now. So suppose that G is cyclic. Let G be a cyclic group. And let's write it as a cyclic group generated by some element A. and let B be some other element of G. Since it is an element of G, then it is some power of A. And what I want to know is, this is a cyclic group of order n, which, as we know, it means that A has order n. And what I want to know is what orders are possible in this group. So A has order n, but what about B? What is the order of B? So it turns out then that the order of B, which is the order of A to the K, will be n divided by the GCD of n and K. Or in other words, it's the order of A divided by the GCD of n, of the order of A and K. Okay, so this gives me a formula for the order of any other element of a finite group that is cyclic. Okay, so here is the proof of this goes as follows. So let M be the order of B, which is by definition is the smallest integer M such that B to the M is E. So that is the smallest integer such that A to the km is E. But we know that this is true. A power of A, it will be E. By our previous result, a power of A will be E if and only if that power is divisible by its order. So what we are actually looking for is for the smallest m, such that the smallest positive integer m, such that n divides k times m. Okay, so that is the integer that I want. So what is that going to be? Well, now let's write the d for the GCD of k and n. Then I can divide n by d and m by d, and still what I want is m to be the smallest, such that n divided by d, which is an integer, divides k times, k is the one that is divisible by k divided by d times m. Okay. However, now, by the way, this is a fact about GCDs, is that the GCD of a number divided by the GCD of A and B then is automatically, that has to be 1. Okay, so because the GCD of n and k is d, this implies that n divided by d and k divided by d are relatively prime. And these two things together, if n over d divides this product and n over d and k over d are relatively prime, then n over d has to divide m. So this n over d has to divide m. This step from here to here is usually what's called Euclid's lemma, which is something very, very useful in elementary number theory. But that is, let me actually state it here, Euclid's lemma. It just says that, so let A, B, C be integers such that 1 A divides BC, and the GCD of A and B is 1, then A divides C. Okay, C is a multiple of A. That's the result. Okay, and that's what I'm using over here, is that these two, this one and that one, are relatively prime. This divides the product, so this one has to divide M. So the smallest integer then that divides, that works, will be precisely when M is exactly N over D. But what is N over D is what we wanted, which is it's N, the order of A, and D is the GCD of K over N. So this is a proof of what we wanted. Okay, so now finally we can do some examples. So let me do some example of what we just proved. We just proved that, remember, G is cyclic, order N, A is a generator, so A itself is of order N. Then the order of a power of A as an element of that group has to be, so the smallest power of A to the K that will give me the identity has to be N divided by the GCD of N and K. So the order of A divided by the GCD of the order of A and K. So let me show you how to use this. Let's look at U7. U7, remember the notation are the units, so things that have multiplicative inverses in Z modulo 7. And the things that have multiplicative inverses in this case are 1 and 2 and 3 and 4 and 5 and 6 modulo 7. Anything except 0 has a multiplicative inverse. And I suggest that you go and find them all. What is the multiplicative inverse of 2? What's the multiplicative inverse of 3, etc.? And let me see. So here's my question: is U7 cyclic? Well, if it is so, then there would be a generator, and a generator would have order 6. So equivalently, I want to know what is the order of each element. And if I find one order 6, then that is a generator. So let's see what is the order of 1. 1 to the 1 is 1, which is the identity in here. So the order of 1 is just 1. That is not a generator. How about 2? Let's look at the powers of 2. 2 squared is congruent to 4 modulo 7. 2 cubed is congruent to 8 modulo 7, and 8 is 1. So the very first time that a number to the that 2 to some number is the identity is 3. So that tells me that the order of 2 is exactly 3. That is not a generator. Let's find what is the order of 3. So 3 squared is 9. 9 is 2 modulo 7. 3 cubed will be 9 times 3, or 2 times 3, which is 6. And 6 is not 1 mod 7, so I keep going. 3 times 6 is 18, and 18 is 14 plus 4. 4 times 3 is 12, and 12 is 5. And 5 times 3 is 15, which is 1. So this was 3, this was 3 squared, this was 3 cubed, this was 3 to the 4, 3 to the 5, and 3 to the 6. So the very first time that a power of 3 gives me 1 is 6. So since I got something of order 6 and U7 has order 6, and you can see that all the powers of 3 go through every one of these units, 1, 2, 3, 4, 5, and 6, then I get that 3 is a generator. So U7 is under multiplication generated by 3. Okay, so now is when I'm going to use this formula to compute the order of every other element. So for example, what is the order, the multiplicative order of 2? So I can compute that as follows. What is the order of 2 in U7? Well, 2 we just found, it is the same as 3 squared. And the formula tells me that the order of a power of 3 will be the order of 3 divided by the GCD of the order of 3 and the power that I'm using, the k, which in this case is the power of 2. Okay. The order of 3 was 6, and then this is the GCD of 6 and 2. The GCD of 6 and 2 is 2, so this is 6 divided by 2, so it's 3. So the order of 2 is 3. What else do we have? What is the order of 6? So, for example, what is the order of 6? 6 is 3 cubed. And the formula now tells me that it will be the order of 3 divided by the GCD of the order of 3, 6, and the power that we're using, which is 3 in this case. The GCD of 6 and 3 is 2 is 3, and 6 divided by 3 is 2. So the order of 6 is 2. And we can check that 6 squared is 36, which is 35 plus 1. So this is 1 modulo 7. So yes, the order of 6 is 2. What are we missing? What is the order of 4 and 5? So let me just do those quickly. The order of 4 is the order of 3 to the 4, which is 6 divided by the GCD of 6 and 4, which is 2. So this also has order 3. And the order of 5 is the order of 3 to the 5, which is 6 divided by the GCD of 6 and 5. 6 and 5 have GCD 1, so this is 6. So it turns out that 5 is also a generator. So U7 is also generated by 5 under multiplication. Okay. So let me just then finish with two results that I'm not going to prove, but you can, using what we've just seen, you can prove. First of all, the generators of z modulo nz and their addition are the integers r such that any integer that is between 1 and n, and the GCD of r and n is 1. So you can check what are the possible generators. Under addition of z modulo nz, they have to be numbers that are relatively prime to n. Otherwise, they will not generate all of z modulo nz under addition, the repeated addition. And another one is that if z modulo p is cyclic, generated by, say, some class G, then the generators, all the generators of z modulo p z cross will be of the form any power of that one generator with the GCD of k and p minus 1 being 1. Because, and this follows from the formula, for the order. We know that the order of G will be all of this, which is actually P minus 1. So this means that the order of G is the size of the group, which is P minus 1. And we know we want another generator, so it will be a power of G that also has order P minus 1. But the order of this, by our formula, will be the order of G divided by the GCD of the order of G and K. The order of G is P minus 1, which is the order we want, and then we want the GCD of P minus 1 and K to be 1. So if this is 1, then the whole thing is P minus 1, and the G to the K would also be a generator. So now we see that the generators have to be powers of the one generator, that the power is relatively prime to P minus 1. Let's see that actually we do have an example right here, because we had U7, which is Z modulo 7Z, where that is prime. There are 6 elements in here, 7 minus 1. We found a generator, 3, and what the result tells me is that the possible other generators will be 3 to the 1 or 3 to the 5, because 5 and 6 are relatively prime. And then we see that indeed 5 has also order 6, so 5 is also a generator. Okay, so that's it for today. And next time we're going to start with a different type of groups, which are called permutation groups.